Something impossible just happened in our solar system. Just days ago, astronomers detected a mysterious new object cutting across space, designated C-2025 V1 Borisov. But here's where it gets strange. This thing appeared perfectly aligned between Earth and the interstellar visitor 2I Borisov, the same cosmic wanderer that once shattered everything we thought we knew about comets. The timing? Uncanny. The location? Too precise to ignore. And the man who found it? That's the most unbelievable part. Gennady Borisov, the same lone astronomer from Crimea who 6 years ago discovered the last interstellar object. Now, somehow, he's found another one. Coincidence? Or are we witnessing something far bigger unfolding right now? Before we dive in, hit that like button, subscribe, and tell us where you're watching from, because what you're about to hear might just rewrite our understanding of the universe.
Chapter 1. The Discovery. We first detected C/2025 V1 Borisov on November 3, 2025. At the time, it carried a temporary identifier, GB000810, the kind of label astronomers assign to newly spotted celestial objects before they know exactly what they're dealing with. Within just a few days, the early data began painting a surprising picture. Its trajectory wasn't normal. It was moving far too quickly for a standard solar system comet at that distance. Right now, the object sits within the constellation Virgo, positioned almost perfectly between 3I Atlas and Earth. If you could view a 3D model of the solar system at this very moment, you'd see something remarkable. 3 glowing points forming a distinct line across the night sky. C/2025 K1 Atlas gleams with a golden yellow hue in Leo. C/2025 V1 Borisov occupies Virgo. And 3I Atlas, also in Virgo, sits slightly offset, but from Earth's point of view, they nearly align in a straight line. The geometry is astonishing. Earth, Borisov, and 3I Atlas all falling into near-perfect alignment. Borisov lies slightly above the ecliptic plane, that flat cosmic disk where most planets orbit, yet the visual configuration remains unmistakable. This isn't a sight that comes around often. Now, let's clarify what we know so far. C/2025 V1 Borisov is currently classified as a comet. Its orbital eccentricity is measured at 1.0095, with a margin of uncertainty around 0.26. That number might not sound significant, but it's crucial. An eccentricity greater than 1 means the object isn't gravitationally bound to the Sun. It's on a hyperbolic path, destined to leave the solar system entirely. That would make it interstellar, a visitor from beyond. But here's the catch. 1.0095 sits right on the threshold. It's so close to 1 that astronomers aren't completely sure whether Borisov truly hails from interstellar space or if it might have emerged from our own Oort cloud, that distant spherical shell of icy bodies surrounding our solar system. If you run its motion backwards, all the way out to around 1,000 astronomical units, far beyond where planetary gravity holds sway, and then recalculate, that same eccentricity could easily drop below 1. In other words, even a slight gravitational tug from Jupiter during its approach could make a once-bound Oort cloud comet appear unbound. Outgassing, the release of vaporized materials, could further skew those readings. So, for now, the majority of astronomers lean toward the idea that Borisov originated within our solar system, from the outermost icy regions rather than interstellar space. Still, what stands out most is the timing of this discovery. Chapter 2. The Geometry. At this very moment, C/2025 V1 Borisov lies between Earth and 3I Atlas. The object was first detected as it rose up from below the ecliptic plane, following a steep, inclined orbit that cuts directly through our line of sight. Its closest approach to the Sun, known as perihelion, will occur on November 16, 2025, roughly 10 days from now. At that time, Borisov will be located well above the ecliptic, almost directly in line with Earth and the Sun. And here's where things get strange. We've been observing 3I Atlas for months. It reached its own perihelion on October 29th, just over a week ago, during a period of intense solar activity. Between October 21st and October 29th, powerful solar flares and coronal mass ejections repeatedly bombarded the comet. The energy output was immense, possibly around 33 gigawatts of solar radiation hitting 3I Atlas at its peak. Yet despite that violent exposure, the comet behaved unexpectedly. It formed a faint coma, the glowing cloud of gas and dust that surrounds a comet's nucleus, but no visible tail. Normally, a comet experiencing that much solar heat would be venting material furiously, producing a bright, sweeping tail stretching millions of kilometers. Instead, 3I Atlas remains subdued. Now, Borisov is appearing right in the middle of this cosmic tableau, and it too lacks a distinct tail. Out of 10 official observation reports submitted to the Minor Planet Electronic Circular, only 2 have recorded any trace of a tail. Most reports note only a coma, with one observer estimating it at 40 arcseconds in diameter and a faint tail around 50 arcseconds, while another measured a 23.4 arcsecond coma and a 72 arcsecond tail. Those inconsistencies are wide. Observers can't seem to agree, and in most cases there's little or no visible tail at all. So what we're looking at are 2 celestial bodies, both in close proximity, both lacking prominent tails, and both exhibiting unusual, subdued activity. There's another curious twist. Borisov is significantly dimmer than 3I Atlas. Its apparent magnitude sits between 13 and 14, faint enough to be invisible to the naked eye and requiring a mid-sized telescope to view as a faint, diffuse glow against the star field. Visual estimates put the coma roughly 2.3 arc-minutes across, about 1/13th the apparent size of the full moon. In actual distance, that corresponds to a gas and dust envelope stretching tens of thousands of kilometers from the comet's core. But what's inside that coma? At this point, we still don't have detailed spectroscopic readings. The discovery is too recent, and larger observatories need time to schedule observations, collect photons, and analyze chemical signatures. Still, based on what we know about similar comets, we can make informed guesses. As a comet nears the sun, frozen compounds, water, carbon monoxide, carbon dioxide, begin sublimating directly from solid to gas, forming the coma we see.
The specific chemical makeup of a comet determines when, how, and to what extent it begins releasing gas. For instance, carbon dioxide sublimates at much lower temperatures than water ice. So if a comet has a high concentration of CO2, it can begin venting gas even when it's still far from the sun, sometimes beyond 5 astronomical units. But if the comet's composition is dominated by water ice, it stays dormant until it gets much closer, typically between 3 and 4 AU. C/2025 V1 Borisov is currently well within Venus's orbit, about 0.46 AU from the Sun at perihelion. At that distance, both water and carbon dioxide should be actively sublimating, releasing vapor into space. And yet, there's still no visible tail. Now, compare that behavior with 3I Atlas. Early data revealed that 3I Atlas was unusually rich in carbon dioxide, showing a CO2 to H2O ratio of roughly 8:1, an extreme value. Most comets in our solar system exhibit the opposite pattern, where water vapor greatly exceeds carbon dioxide. This abundance of CO2 caused 3I Atlas to wake up early, forming a coma while it was still beyond Jupiter's orbit. By late September, as it moved past Mars's orbit, that ratio began to shift. Suddenly, enormous amounts of water vapor started streaming from the surface, equivalent to the output of a high-pressure fire hose. It was releasing far more water than what scientists typically see from comets at that distance. And then came the metallic surprise. During summer observations, astronomers detected the presence of nickel in the coma of 3I Atlas, but not iron. That's bizarre. Normally, these two metals appear together because they originate from the same stellar processes, both forged in the hearts of dying stars and later scattered through supernova explosions. These metals become incorporated into new planetary systems as they form. But 3I Atlas broke that rule. It showed nickel without iron, about 4 grams of nickel per second, until late September when iron suddenly appeared. After that, the ratio shifted to a more typical balance. It was as if the comet was slowly becoming more normal over time, but in a strangely delayed and unpredictable fashion. So naturally, the question arises, does C/2025 V1 Borisov exhibit similar traits? At the moment, we simply don't know. But its absence of a visible tail mirrors what we saw in 3I Atlas, and its faint brightness implies that it might be a smaller body, possibly composed of different materials. Chapter 4. The Trajectory. To grasp what's truly going on, we need to examine the orbital paths. C/2025 V1 Borisov follows an orbit inclined at approximately 112.72 degrees relative to the ecliptic plane. That's steep, extremely steep. Most comets within the solar system orbit at angles below 90 degrees, meaning they travel roughly in the same direction as the planets. Once an inclination exceeds 90 degrees, it becomes a retrograde orbit. The object is moving against the flow. Borisov's perihelion distance, the closest it gets to the Sun, is 0.46 AU. That's very near, even closer than Mercury's average orbit. When it reaches that point on November 16, 2025, it will endure intense solar radiation. Any volatile ices near its surface should vaporize rapidly, possibly producing a much more noticeable coma or tail. Now compare that behavior to 3I Atlas. Its perihelion took place on October 29th at 1.36 AU, just inside Mars's orbit, much farther from the Sun than Borisov's path. And yet, despite being more distant, 3I Atlas is significantly brighter. Why? Part of the answer lies in its size. Hubble data suggests that 3I Atlas measures somewhere between 1.4 and 5.6 kilometers across, making it far larger than the typical comet nucleus. A bigger nucleus means more surface area for sublimation, and that translates to greater brightness. But size isn't everything. Activity plays a huge role. A comet that's vigorously venting gas and dust reflects more sunlight and appears brighter. So if 3I Atlas is extremely active while Borisov remains subdued, that would easily explain the contrast. Composition is another key factor. If Borisov's surface materials are darker, less reflective, or contain fewer volatile compounds, it would naturally appear dimmer. Yet one of the most critical clues lies in their orbital planes. C/2025 V1 Borisov's orbit is tilted about 113 degrees, while 3I Atlas follows an orbit inclined only 3 degrees from the ecliptic. That means they travel on nearly perpendicular paths through space, moving in almost opposite directions. This is crucial. If Borisov had actually originated from 3I Atlas, say as a fragment or ejected piece, their orbits would share similar characteristics. But they don't. The planes are orthogonal, their inclinations wildly different. From Earth's perspective, however, they happen to appear close together in the night sky. But that's an illusion, a projection effect. Two objects moving along drastically different paths can seem nearby if the observer's angle happens to align just right. They aren't truly close in physical space, but the geometry remains fascinating. Chapter 5. The Solar Activity Connection. Now let's turn our attention to the Sun. In recent weeks, solar activity has been unusually high. Several powerful sunspots on the Earth-facing side have been releasing coronal mass ejections and solar flares, hurling charged particles across the solar system at hundreds of kilometers per second. On October 21st, just before 3I Atlas reached perihelion, the Sun fired off a major CME directly in its direction, followed by several more over the next week. During its closest approach, the comet endured multiple solar storms in rapid succession. Here's where it gets intriguing. During that same period, another comet, 6 Lemon, was positioned in alignment with the active sunspot region. Essentially, those sunspots were facing directly toward Lemon and 3I Atlas, both lying along that same solar meridian. Now, as mid-November approaches, a new alignment is forming. C/2025 V1 Borisov is nearing its own perihelion, and the same chain of sunspots continues to rotate across the sun's visible surface. If the cycle continues, Borisov could soon find itself in the direct line of fire of solar storms as well. This brings us to a fascinating question. Could solar activity itself be influencing these comets? We already know that solar radiation and solar wind affect comets profoundly. The pressure from photons and charged particles pushes gas and dust away from their comas, forming tails. Intense solar events like CMEs can strip material off a comet's surface, alter its brightness, or even break it apart entirely. But there's a more controversial hypothesis, that planetary alignments might somehow influence solar activity. Some researchers propose that gravitational tugs of planets and even comets could subtly destabilize the sun's magnetic field, triggering increased flare events. Most solar physicists dismiss this idea. The gravitational forces involved are minuscule compared to the sun's internal magnetic dynamics. But even skeptics can't fully ignore the timing. It's uncanny. 3I Atlas reached perihelion right as solar storms peaked. Now, just weeks later, Borisov approaches perihelion while those same active regions persist. If Borisov experiences a CME strike within the next several days, it would strengthen that apparent correlation. Though whether it's causal or coincidence remains unknown. For now, all we can do is wait and watch. Chapter 6: The Speculation. Now, let's address what many people online have been whispering. The idea that C/2025 V1 Borisov isn't a natural comet at all. Some claim it was deployed by 3I Atlas, that it might be an artificial probe designed to observe Earth or collect data from the inner solar system.
This theory started gaining attention because of its timing. The moment 3I Atlas arrived, it passed remarkably close to Mars, Venus, and Jupiter. Then it hit perihelion, the point in its orbit nearest the Sun. Only a few days later, astronomers spotted another mysterious object positioned directly between 3I Atlas and Earth. Now, if someone were trying to send something from an interstellar craft toward Earth, the setup would make sense. You wouldn't want the main vessel coming too close, that's far too risky, and increases the chance of detection. Instead, you'd release a much smaller probe that could quietly travel toward Earth while the larger craft kept moving out of the solar system. But here's where the theory breaks down. The physics just doesn't add up. As Avi Loeb pointed out, the orbital paths of 3I Atlas and C/2025 V1 Borisov don't intersect or even approach one another. There's no moment where they align closely enough to make the launch scenario possible. Even the slight non-gravitational acceleration detected in 3I Atlas, that tiny deviation from its expected gravitational path, is far too weak to send anything toward Borisov's current position. For 3I Atlas to actually fire off a probe that could reach C/2025 V1 Borisov, it would need to release it with tremendous force, giving the probe a velocity change of several kilometers per second. That kind of thrust would be unmistakable. Yet, no one has detected any propulsion signature. No jets, no thermal flare, no sudden course correction beyond normal cometary outgassing. So, the simplest and most likely explanation remains that C/2025 V1 Borisov is exactly what it appears to be, a natural comet originating from the Oort cloud, traveling through the inner solar system on a highly eccentric orbit. Still, let's indulge the what if for a second. What if 3I Atlas did deploy something? What if the propulsion system was subtle enough to escape detection? Chemical rockets could produce thrust without an obvious exhaust plume. Ion drives could slowly accelerate a small probe with faint emissions almost impossible to spot from Earth. But again, there is no evidence of this. What we have is a suspicious-looking alignment, two comets with muted tails, and some curious timing. But in science, we don't draw conclusions from coincidence. We rely on data. And right now, the data points to one conclusion: a natural origin unrelated to 3I Atlas. That said, it's still worth paying attention. Even if the extraterrestrial hypothesis is wrong, and it almost certainly is, the observations themselves are strange enough to merit attention. Chapter 7. The Brightness Anomaly. Let's take a closer look at the brightness puzzle. C2025 V1 Borisov has an apparent magnitude between 13 and 14, faint, barely within the range of mid-sized amateur telescopes. Meanwhile, 3I Atlas shines much brighter, at around 9.8 magnitude, over 1,000 times more luminous. Remember, magnitude is a logarithmic scale. Each step equals roughly 2.5 times brightness difference. So a 3 to 4 magnitude gap means one object appears 15 to 40 times brighter than the other. Now here's the odd part. 3I Atlas is currently farther from the Sun than C2025 V1 Borisov will be at its closest point, yet Atlas is far brighter. Part of that difference can be explained by size. A larger nucleus reflects more sunlight. But activity also plays a key role. 3I Atlas has been described as unusually bright for its distance. Observations showed its luminosity increasing 5-fold between May and June 2025, when, by basic orbital math, it should have only increased 1.5 times based on its approach to the Sun. Something was triggering additional outgassing, possibly frozen gases suddenly sublimating, ejecting clouds of dust and vapor, rapidly expanding its coma. But curiously, it didn't form a long tail. Instead, it produced what astronomers call an anti-tail, a short jet of material pointing toward the Sun rather than away from it. It's rare, but not unheard of. A few comets have shown similar traits. Yet for 3I Atlas, the anti-tail was particularly striking. By September, that anti-tail had reversed direction, turning into a normal tail pointing away from the Sun. The comet was evolving, behaving more like typical comets as it approached perihelion. Then came the solar storms, bursts of charged particles, and intense radiation, the kind of environment that usually causes comets to flare dramatically with long, glowing tails. But 3I Atlas did not. It remained bright, yes, even brighter than expected, but no long, sweeping tail, only a short fan-shaped plume vaguely directed away from the Sun. Now, with C2025 V1 Borisov nearing its own perihelion, the question arises, will it behave the same way? Will it brighten dramatically without forming a classic tail? We don't know yet. If it does, that would suggest both comets share some unusual composition. Maybe they're made of materials that don't produce extended dust tails. Maybe their dust grains are too heavy to be swept away by the solar wind. Maybe their volatile elements sublimate cleanly without dragging much dust along. Or maybe there is something we still don't understand. Chapter 8. The Composition Mystery. Now, let's explore what these two objects are made of. 3I Atlas, according to spectroscopic data, is unusually rich in carbon dioxide, with a CO2 to H2O ratio of about 8 to 1. That's essentially the reverse of what we see in most comets from our solar system, where water is the dominant volatile and CO2 only appears in small amounts. This high CO2 content explains why 3I Atlas became active so early. Carbon dioxide sublimates at far lower temperatures than water ice. Dry ice begins to vaporize around 73 Kelvin, minus 195 degrees Celsius, whereas water ice needs to reach roughly 150 Kelvin, minus 123 degrees Celsius. So a CO2-rich comet will start venting gas much farther from the Sun, sometimes beyond 5 astronomical units. And that's exactly what happened. 3I Atlas began forming a coma near Jupiter's orbit long before water ice could have thawed. But then, something shifted. As it moved inward, water emissions suddenly spiked. By late September, the amount of water vapor it released was far higher than predicted. The CO2 to water H2O ratio began to flip, making it behave more like a typical comet. Then came another surprise: metal vapor. Astronomers detected nickel in the coma early on, but found no iron. That's highly unusual. Nickel and iron are cosmic siblings. They form together in supernovae and usually appear side by side in comets and asteroids. Yet here, 3I Atlas was venting nickel, about 4 grams per second, without any detectable iron. Some researchers propose this might be due to nickel carbonyl, a volatile compound that forms when nickel metal reacts with carbon monoxide. It's common in industrial chemistry on Earth, but has never been seen in a natural comet before. Later, iron finally showed up, and the ratios normalized. 3I Atlas began behaving more like an ordinary comet again. So now the big question, what about C2025 V1 Borisov? We don't have spectral data yet, but if it shows the same pattern, delayed water release, CO2 dominance, strange metal signatures, it could hint that both comets were born in similar conditions. Not necessarily from the same parent body, but possibly from the same type of environment, perhaps a distant, carbon-rich region at the edge of another star system.
Maybe both comets formed in regions of their original planetary systems rich in carbon dioxide, places where frozen CO2 was abundant and water ice was scarce. Maybe they both spent billions of years preserved in the distant Oort cloud, deep frozen relics of early formation. Or maybe they wandered separately through interstellar space, carrying with them chemical fingerprints of entirely different origins. It's also possible that the resemblances we're seeing are just that, coincidences. We'll have much clearer answers once ongoing spectroscopic studies finish and reveal what these bodies are truly made of. Chapter 9. The Imaging Campaign. Right now, observatories across the globe are tracking C2025 V1 Borisov. Despite its faintness, it's still within reach for skilled observers. Amateur astronomers equipped with 6-inch telescopes have successfully captured it using stacked long exposures to reveal the soft glow of its coma. The resulting images show what's essentially a fuzzy sphere, a circular blur with no distinct tail, aligning perfectly with telescope-based visual observations. One observer, who goes by AlphaRats on X, formerly Twitter, posted a composite image from November 3rd. In that image, the background stars appear stretched into streaks because the frames were aligned with the comet's motion, keeping the comet crisp while smearing everything else. C2025 V1 Borisov appears there as a dim, rounded smudge, maybe slightly elongated in one direction, though that's open to interpretation. No dramatic tail, no sharp jet, just a hazy coma. Another observer recorded the comet a day earlier and reported similar results. No significant tail, consistent brightness, and a magnitude hovering between 12 and 14, depending on atmospheric conditions and instrument sensitivity. Now contrast that with recent post-perihelion images of 3I Atlas. On November 5th, a Spanish observatory obtained what's currently our clearest view after its closest solar approach. The picture reveals a bright coma showing faint elongation away from the sun. There's a trace of a tail, barely visible, but nothing close to the sweeping, dramatic streaks people usually associate with comets. This muted appearance is surprising, especially considering that 3I Atlas had just endured a week of intense solar storms, passing perihelion at 1.36 AU. Under that much radiation, most comets would flare brilliantly, forming striking photogenic tails. For example, the famous Hale-Bopp comet in 1997 displayed a massive glowing tail visible to the naked eye, but it came much closer to the sun, around 0.9 AU. 3I Atlas, by comparison, stayed roughly twice that distance, so perhaps this is simply a distance factor. Maybe both 3I Atlas and C2025 V1 Borisov are behaving according to normal physics. Their tails just appear smaller because they're farther from the sun. But if that's the case, then another mystery emerges. Why is 3I Atlas so bright despite shedding so little dust? The answer likely lies in gas. 3I Atlas is venting enormous amounts of volatile gas, primarily CO2, water vapor, and carbon monoxide. These gases scatter sunlight efficiently, making the comet appear luminous even when the dust component is minimal. Dust is what usually forms a visible tail. Gas, on the other hand, creates a glowing coma that's harder to see without specialized filters. This explains why the tail looks faint. It's simply a gas-dominated comet. If C2025 V1 Borisov exhibits the same pattern, that would explain its nearly tailless look too. It's not inactive, it's just producing far more gas than dust. We'll only know for sure once full spectroscopic readings come in. Chapter 10. The China Release. On November 6th, the Chinese Space Agency finally released long-awaited photos of 3I Atlas captured by the Tianwen probe in Mars's orbit. These images were taken during the comet's close pass by Mars in early October, when it came within about 30 million kilometers of the planet. The excitement surrounding these images was enormous. Astronomers had been anticipating high-quality data, but when the photos dropped, disappointment followed. The visuals were low-resolution, pixelated, and grainy. 3I Atlas appears only as a bright, fuzzy blob crossing the Martian sky. A faint suggestion of a trailing feature can be seen, but any real structure is lost in the poor image quality. Many scientists expressed surprise, given that Tianwen's cameras are technically capable of much higher detail. The prevailing theory is that the images were heavily compressed or downsampled before release, possibly to save data bandwidth or due to internal policy restrictions. It's also possible that the comet was simply too faint for Tianwen's optical sensors to capture with clarity. Whatever the cause, the result is underwhelming. The only clear takeaway is confirmation. 3I Atlas was indeed there. It had a coma and perhaps a short tail, but the finer details are obscured. Now, all eyes turn towards NASA. The Mars Reconnaissance Orbiter, MRO, also captured images of 3I Atlas with its HiRISE camera, one of the most advanced imaging instruments ever deployed beyond Earth. HiRISE can resolve features as small as 30 centimeters on the Martian surface. Even from 30 million kilometers away, that translates into significantly sharper imaging potential than what Tianwen delivered. However, NASA's images remain unreleased. Due to the US government shutdown that began on October 1st, NASA's communications division has been placed on furlough. The scientific teams continue working behind the scenes, but the public-facing departments responsible for data publication are inactive. This bureaucratic delay has frustrated astronomers and sparked speculation among online communities. Some claim NASA might be withholding the images because they reveal something unexpected, but there's no credible evidence to support that. The far more likely explanation is purely procedural. The government is offline, and the release team is simply not working. Representative Anna Paulina Luna even sent a formal letter to NASA's acting administrator, Sean Duffy, urging for the immediate release of the 3I Atlas imagery. Duffy responded that the photos would be made public once the shutdown ends. Until then, everyone waits, both scientists and the curious public alike. Chapter 11, The Light Curve. Let's examine how the comet's brightness evolved over time, its light curve. A light curve is simply a graph showing how bright an object appears as it travels through space. For comets, brightness usually rises as they approach the sun due to increased sublimation and fades as they move away. 3I Atlas has been tracked since July 2025, and its light curve reveals intriguing deviations. Initially, in July and August, it appeared faint, with an apparent magnitude between 12 and 13, which fits expectations for a comet still orbiting beyond Mars. Then, in early September, something changed. Its brightness began climbing much faster than predicted. Based on orbital models and distance from the Sun, astronomers estimated it should reach a magnitude around 11.2 by late October. Instead, it reached 9.8, significantly brighter. A 1.4 magnitude difference may not sound huge, but in astronomical terms, that's roughly 2.5 times more luminous than expected. Such rapid brightening is highly unusual. Most comets follow a predictable pattern: gradual increase near the sun, then steady dimming as they depart. But 3I Atlas broke that trend completely. It brightened far faster and far more dramatically than simple models allow. Why? One possible explanation is a cometary outburst, a sudden spike in activity when buried pockets of volatile gases under the surface are suddenly exposed to sunlight, releasing material explosively.
Perhaps the gas within the comet's core sublimated suddenly, dragging fine dust particles outward and briefly increasing its brightness. Yet if that were the case, astronomers would expect to see some visible proof, a noticeable swelling of the coma or a spike in dust output. But that's not what the images show. The coma remains relatively steady, displaying no clear signature of an outburst. Another potential explanation lies in surface evolution as the comet warms. Maybe its outer icy crust vaporized, revealing more reflective subsurface material. Or perhaps the balance between gas and dust release shifted, causing sunlight to scatter more through gas molecules rather than being absorbed by dust. This would align with observations suggesting that 3I Atlas is producing abundant gas, but very little dust. Gas reflects sunlight effectively, boosting brightness without forming a long, obvious tail. But there's one more theory, and it's the one drawing the most debate: non-gravitational acceleration. Chapter 12: The Acceleration Debate. In late October, NASA revised the orbital calculations for 3I Atlas, revealing that the comet had experienced a non-gravitational push near its closest approach to the Sun. That in itself isn't extraordinary. When comets vent gas, the escaping jets create a minute but measurable thrust, nudging the nucleus off its purely gravitational path. Typically, the strength of this thrust correlates well with the quantity of gas escaping, predictable and calculable. But 3I Atlas didn't fit the math neatly. NASA's tracking data showed the comet was displaced by about 4 arcseconds from its predicted location near perihelion. A small difference, but large enough to be significant. When scientists calculated the outgassing needed to cause that deviation, the results were astonishing. The comet would have had to lose between 10 and 20% of its total mass. That's enormous. For an object several kilometers wide, it implies billions of tons of material expelled into space. If that had happened, we should see a vast cloud of debris surrounding it, a glaring, unmistakable halo. But there isn't one. The coma looks modest. There's no sprawling debris field or giant gas plume. Astrophysicist R.V. Lobo addressed this inconsistency, suggesting that if the acceleration is genuine, but the missing gas cloud isn't, then perhaps something other than natural outgassing caused the thrust. In a post dated November 1st, he proposed an unsettling hypothesis. If 3I Atlas truly shed that much mass, the residual gases and dust should still linger nearby. They wouldn't just vanish. If those traces remain undetectable even after the comet reappears in December, it would mark what he calls the 10th anomaly, 9 oddities already observed, plus a missing debris field. The alternative, he wrote, is that the acceleration arose from a more efficient propulsion mechanism, one that doesn't require ejecting such massive quantities of material. Conventional chemical rockets, for instance, expel exhaust at speeds of 3 to 5 kilometers per second, about 10 times faster than natural comet outgassing. Ion drives can go even further, reaching velocities between 10 and 50 kilometers per second. With faster exhaust, far less material is needed to achieve the same impulse. In theory, if 3I Atlas had some kind of propulsion system, purely hypothetically, it could produce the observed motion without leaving a conspicuous gas trail. Yet this idea brings its own complications. Artificial thrust should generate visible clues: a jet plume, a rotational change, or a thermal hotspot from an active engine. None of these are observed. The object still looks and behaves exactly like a comet. Apart from its unusual chemistry and faint tail, everything else fits comfortably within known cometary physics. And now, the most recent orbital updates from NASA tell a slightly different story. As of November 5th, the measured acceleration appears smaller than first estimated. Revised models show a weaker deviation, implying the comet may have lost only about 5 to 10% of its mass, far less than early projections. That reduction also means the missing cloud might simply be too faint to detect, especially if it's composed mostly of transparent gases that don't reflect much light. For now, the acceleration debate remains unresolved. The data fits multiple explanations, none conclusive. The final word will have to wait until 3I Atlas emerges from behind the Sun in early December. When it does, astronomers will compare new images, check for any debris cloud, and reassess its motion. If the cloud is present, the natural outgassing theory holds. If not, we may be facing a genuine cosmic mystery. But what does all of this mean for C/2025 V1 Borisov? Chapter 13: The Coincidence Problem. Here's where things get truly intriguing. On one hand, we have 3I Atlas, an interstellar visitor behaving oddly, brightening unexpectedly, emitting unusual gases, and accelerating for unclear reasons. It reaches perihelion on October 29th. Just days later, a second object appears, C/2025 V1 Borisov. This new arrival emerges between 3I Atlas and Earth, sharing some eerily familiar traits: no striking tail, modest brightness, and peculiar gas activity. The timing feels too neat to ignore. The positioning seems deliberate, and the parallels in behavior spark countless questions.
Yet, orbital dynamics crushed the notion of a physical link. Their trajectories never intersected. Their paths are nearly perpendicular. Even if 3I Atlas had ejected material at incredible speeds, its modest acceleration couldn't possibly send anything toward Borisov's region of space. So if they're unrelated, why do they appear so similar and so close in time? The simplest answer might be observer bias. Astronomers and enthusiasts worldwide have been fixated on 3I Atlas, directing countless telescopes toward its sector of the sky, the constellation Virgo. That intense focus naturally increases the odds of spotting another faint object nearby. In other words, C/2025 V1 Borisov may have been noticed not because it's extraordinary, but because attention was already concentrated exactly where it appeared. Without 3I Atlas, Borisov might have slipped under the radar for weeks or even months. Its faintness makes it unlikely to appear in most automated surveys until it grew significantly brighter. As for the discoverer, Gennady Borisov, his track record speaks volumes. The same amateur astronomer who discovered 2I Borisov back in 2019 with a homemade telescope in Crimea has spent years scanning the heavens methodically, hunting for faint, fast-moving objects. His dedication and skill make his latest find unsurprising. So, while the timing raises eyebrows, the discovery itself may be nothing more than a coincidence born from vigilance and circumstance. Still, for those watching the sky, it's hard to shake the feeling that something about these twin visitors, one known, one new, might be telling us there's more to this cosmic story than meets the eye.
The timing of this discovery, coming just days after 3I Atlas reached its perihelion, has drawn plenty of attention. Both of these celestial bodies share something peculiar. Neither displays a distinct sweeping tail. Their proximity in the sky only deepens the intrigue. These aren't conclusions, merely observations. Yet in science, even fragments of data deserve examination. We don't ignore clues simply because they challenge our assumptions or suggest possibilities we find uncomfortable. We gather evidence, we study it carefully, and we wait for more. Which brings us to the next phase. What happens now? Chapter 14, The Observation Window. C/2025 V1 Borisov is currently visible in the early morning hours, hovering low on the eastern horizon before sunrise. It resides in the constellation Virgo, near the same region of the sky where 3I Atlas was last seen. For astronomers, this alignment presents an extraordinary opportunity. Two mysterious objects, both observable within the same field of view. Adding to this cosmic lineup, C/2025 K1 Atlas, that bright golden-yellow comet in Leo, is also close by. So if you're fortunate enough to have a clear eastern horizon and a telescope with at least an 8-inch aperture, you could glimpse all three at once. But time is running short. C/2025 V1 Borisov is currently moving rapidly toward its perihelion, which it will reach around November 16th. As it draws nearer to the sun, sunlight will soon overpower it, washing it out of view. By late November, it will vanish into the solar conjunction, just as 3I Atlas did not long ago. Meanwhile, 3I Atlas is projected to reappear in mid to late November, emerging once again from behind the sun and returning to visibility in the pre-dawn sky. When that happens, astronomers will resume their study, measuring its coma, searching for the missing gas cloud, and determining whether the strange acceleration it experienced can be explained by normal outgassing. They'll also compare it closely to C/2025 V1 Borisov. If Borisov displays similar behavior, brightening quickly, lacking a defined tail, and exhibiting unusual spectroscopic patterns, it would strengthen the idea that these two objects belong to a shared category, possibly comets from the far reaches of the Oort cloud, or even something with an entirely different origin story. On the other hand, if Borisov behaves like a typical comet, developing a clear tail, showing standard chemical makeup, and following predictable brightness trends, then the likenesses between them were nothing more than chance. In that case, C/2025 V1 Borisov would simply be another Oort cloud visitor, its timing just an uncanny coincidence. We'll have answers soon. Spectroscopic data collection is already underway. Several major observatories have placed Borisov on their observation lists. Over the coming weeks, new information will begin to flow in.
And by December, when both 3I Atlas and Borisov are once again visible together, scientists will finally be able to make direct comparisons. Chapter 15: The Broader Context. Now, let's take a step back to view the bigger picture. We're in the midst of an unusually active season for comets. In just a few short months, multiple new ones have entered the inner solar system. C2025 K1 Atlas, glowing a warm gold in Leo, the faint A6 Lemon near the sun's glare, the enigmatic 3I Atlas, and now C2025 V1 Borisov. While the sight of comets isn't uncommon, dozens appear every year, most pass by unnoticed. They're faint, unremarkable, and rarely capture global attention. But this time feels different. Part of that due to 3I Atlas. Its suspected interstellar origin sets it apart as only the third object of its kind ever confirmed. Its strange attributes, its composition, unusual brightness pattern, and lack of a tail have triggered intense investigation. Yet another factor lies in the timing and geometry. Several rare comets appearing in roughly the same region of the sky around the same time during a period of heightened solar activity. The coincidences weave an enticing narrative, and as humans, we can't resist patterns. Even scientists aren't immune to that impulse. We search for links, sometimes where none exist. We interpret trends, test ideas, and occasionally we're proven wrong. The supposed connection dissolves into randomness. But sometimes the patterns hold true, revealing something entirely new about our universe. That's the delicate balance here with 3I Atlas and C2025 V1 Borisov. The question remains open. Are the similarities meaningful, or are they just statistical noise? We don't yet know. So, as always, the scientific path is clear. Collect more evidence, test every hypothesis, and stay humble enough to accept that we might be mistaken. Chapter 16: The Interstellar Question. Now we arrive at the central mystery. Is C2025 V1 Borisov actually interstellar? Current orbital calculations give it an eccentricity of 1.0095 plus or minus 0.0026. If that number holds above 1, it means the object isn't gravitationally bound to our sun, implying an interstellar origin. But if it dips below 1, then it's native to our solar system, most likely from the distant Oort cloud. Right now, uncertainty clouds the result. The margin of error leaves room for either possibility. Still, most astronomers lean toward a solar system origin, and here's why. When the orbit is traced backwards, accounting for the gravitational influences of major planets, the eccentricity tends to decrease slightly. Even a minor gravitational nudge from Jupiter near perihelion can shift a comet's path from hyperbolic, interstellar, to elliptical, bound. Similarly, jets of gas from outgassing can push the orbit in the opposite direction, creating the illusion of a hyperbolic trajectory. So, with an eccentricity near 1.0095, Borisov sits right on the edge. It could genuinely be a wanderer from another star system, or it could simply be a long-period comet on a stretched elliptical orbit that only appears hyperbolic. There's historical precedent for this ambiguity. Many new comets entering the inner solar system for the first time have eccentricities hovering around 1, some slightly above, others slightly below. Distinguishing between the two categories is notoriously difficult. The critical difference lies in long-term motion. If scientists simulate the comet's orbit millions of years backwards, including effects from galactic tides and passing stars, they can determine whether it was ever bound to the sun. If it was, it's an Oort cloud comet. If not, then it truly hails from the stars. As for C2025 V1 Borisov, such analysis is still underway. The discovery is too recent for final conclusions. Astronomers need more data to refine the orbital path and run detailed simulations. Early results, however, suggest it's likely a solar system object. Its inclination of about 113 degrees is steep, but not beyond the known range of Oort cloud comets. Its perihelion distance around 0.46 AU is tight, but not extraordinary. All evidence so far points to a typical long-period comet making its first inner solar system visit in millions of years. And yet the timing, emerging so soon after 3I Atlas, keeps curiosity alive. If C2025 V1 Borisov is definitely bound to the Sun, then the near-simultaneous arrival of two peculiar comets may just be coincidence. Improbable, but possible nonetheless.